Good morning, students. We are continuing with the discrete time Markov chain. So last time we have started with the limiting probability. So let me continue that. Okay, so last time we started with an example where which is the application basically of discrete time Markov chain. This is the no claim discount system. The example we have taken. So we have discount level E0, E1, E2. E0 means no discount, E1 means 20% discount, E2 means 40% discount. And this is basically uh, for insurance basically of. Okay, so now for example, if insurance of some motorcycle or car is there, so if some claim is made, based on that level shifted. So movement in the system determined by the rule whereby the one step back discount level or stays E0 with one claim in each year and return to the level of no discount if more than one claim is made. Okay, a claim free year results in one step to the higher discount level or remain in class E2 if already there. So this is the LCD system. If we suppose that anyone in this system has the probability one claim in a year is 0.2, while the probability of two or more claim is 0.1. So based on that, last time we have constructed the TPM, which is basically it remains in E0. If it is in E0, then finally it will be in E0 with the probability 0.3. Means zero discount is there. That means if one claim or more than one claims are there, that means 0.2 plus 0.1, 0.3, and it move to one higher discount level with probability, because it can move to one higher discount level. So with probability 0.7, other will be 0.2, and similarly other we also determine. This is the TPM basically. Now in long run, what proportion of time is the process in each of three discount classes? So whether can anybody tell whether this TPM is regular? So we have 0, 1, 2, 0 to 0 we can stay, then 0 to 1 we can go, then 1 to 0 we can come, and then 1 to 2 we can go, 2 to 0, and 2 to 2, 2 to 1, and 2 to 2 is there. So this is irreducible, okay, aperiodic and finite state Markov chain. All right, because all states are connected to each other, and aperiodic because, for example, in state 0 we will GCD of 1, 2, 3 and so on. So aperiodic and finite state. So can you now say whether this is regular?
Yes, sir.
Yeah, so we know that Last time we have stated that if these conditions are satisfied, finite state aperiodic irreducible Markov chain is regular and recurrent. So either you can do this thing. So we can say from here it is regular, or you can just make like this also, plus plus 0 plus 0 plus 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 plus, multiply this with p. So in this fashion you can continue. So this will be plus, next value is plus, next value is plus, 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 plus. So p, this is p square. So this is regular clearly. From here also we can say regular. And this also implies that this is regular. So once regular, so then we know that for a regular TPM, limiting probability exists, and solution is given by pi is equal to pi p, which is summation pi k is equal to 1. So then, so basically pi is pi naught, pi 1, pi 2, where pi naught basically 0, 0 may here means E0, E1, E2. Okay, so pi naught means pi E naught, pi 1 means pi E1, pi 2 means pi E2. That is in the long run, it will be in state E1, E naught with probability pi naught. So we know that pi is equal to pi p, such that summation pi naught plus pi 1 plus pi 2 is equal to 1. Okay, so we can just say this is pi naught, pi 1, pi 2, pi naught, pi 1, pi 2, and okay, so this is p is your 0 0.3, 0 0.70, 0 0.3, 0, 0.7, 0.1, 0.2, 0.7. Okay, and pi naught plus pi 1 plus pi 2 is equal to 1. So we need only 3 equations. So one equation is this, and 2 equation we will take from here. So that will be pi naught, that means pi naught is equal to 0 0.3 pi naught plus 0 0.3 pi 1 plus 0 0.1 pi 2, then pi 1 is equal to 0 0.7 pi naught plus, okay, plus other will be 0 and 0 0.2 pi 2. Only 2 equation we will take here. Okay, because three unknowns are there, and pi naught plus pi 1 plus pi 2 is equal to 1. So these 3 equations. Okay, so don't take 3 equations from pi is equal to pi p. In this case, if pi is, let us say, 4, pi naught, pi 1, pi 2, pi 3, then 3 equations from pi is equal to pi p, and one equation is this pi naught plus pi 1 plus pi 2 plus pi 3 is equal to 1, like that. So based on that, okay. So now you solve this. So you will get pi naught is 0.1860, pi 1 is 0.2442, pi 2 is 0.5698. So This is pi naught is the probability that the NCD system will be in state E naught in the long run. This is 0.1860. Pi 1 is the probability that in the long run the process will be in state E1. That means with the 20% discount. That is annual premium is rupees 80. And pi 2 is that. Okay. So now find the average annual.
Sir,
Yes.
sir, in previous part, how state E1 is aperiodic?
Pardon, what you are asking?
How E1 is aperiodic in the diagram you made?
Yeah,
Its period
because
is
we
2,
need
na?
to, no, because these are basically uh, 0 is communicating with 1, which is communicating with 2. Okay. So period of 0, 1 and 2 are same. And period of 0 is GCD of 1, comma 2, comma 3, comma so on, because we have to see collect GCD of all positive integers such that PII positive integer n such that PIN is positive.
But sir, for E1, it is coming out to be 2.
No, it is not coming out to be 2 because these are basically because this is you can write down this thing also. This D1 is GCD of 2, 3, 4, 5, 6, 7, so on.
Yes, sir. Sorry, sir. Yeah, got it.
So like that also you can write down. Also you can just state from because they are communicating with each other. So therefore their period will be same. Okay. Now,
So you had said that you will come up with the proof of
yeah,
that
proof
thing.
already I have provided. You can just see the notes.
Okay.
Yeah. Find the average annual premium paid. So now average annual premium will be summation PIXI. So that will be he will pay 100 rupees if he is in state E naught, 80 rupees in state E1, 60 rupees in state E2. So that means 100 into 0. Into pi naught 0.1860, 80 rupees into pi 1 0.442 plus 60 rupees with probability 0.5698. So this is coming out to be 72.324. So this is the answer here. So this is the this much rupees the average annual premium paid. Now this pi is equal to pi p if we solve this we called as stationary if we don't know the whether in general if we have let us say uh, periodic because we are talking about here a periodic also. So if we have periodic then we may have sub TPM we may have. For example, this is the TPM, this is the TPM, this value may be 0 like that. Okay, then we may have solve pi is equal to pi p here. Let us say this is basically sub TPM is basically regular here, and this sub TPM is regular. We can solve pi is equal to pi p here, and then this is known as the stationary distribution basically. So if we solve pi is equal to pi p and summation pi k is equal to 1, this solution of pi, then pi is known as the stationary probability distribution. And in general, if we are finding the limiting probabilities, these are known as the limiting probabilities, limit of that, as we have defined the in the fashion of limit basically, limit of this. But for regular TPM, the stationary probability and limiting probabilities are basically same. Okay, so stationary means this pi p is equal to pi p, summation pi I is equal to 1. We are solving, answer we are calling as stationary probability. Okay, and if we are finding out the limiting probabilities, limit of these, limit as goes to infinity, pijn is equal to pi j, then these are known as basically limiting probabilities. So for regular TPM, limiting probabilities and the stationary probabilities are both basically same thing. Now, okay, now let us see for doubly stochastic matrices. So a TPM is doubly stochastic, is doubly stochastic if column sum, column as well as column sum as well as row sum as well as column sum is 1. Okay, so that means this sum is 1, this sum is 1. Okay, so that means column sum to 1 as well as rows. Okay, because row sum we know that is already 1. If the column sum is also 1, then we say that corresponding TPM is basically a doubly stochastic, or corresponding TPM is doubly stochastic basically. Okay, so P, so we have, let us say P is doubly stochastic, elements are Pij. So that means summation of Pik, summation over K, summation over P Kj, summation over K is 1 for all Ij. That means sum of rows as well as sum of columns are sum of each row and sum of each column is basically 1. So now consider a doubly stochastic TPM of n states. Let us say that states are n states are there. Let us say that matrix is regular. Okay, we have regular TPM or regular Markov chain. Then we are claiming that then the unique limiting distribution is the uniform distribution. That means pi is equal to 1 by n, comma 1 by n, comma 1 by n, because n states are there, total n states are here. because there is only one solution. Why this is? Because we know that there is only one solution. One solution, pi j is equal to summation k pi k pkj. Summation pi k is equal to 1 from the last theorem. Because we know that for the regular TPM, pi is equal to pi p and summation pi k is equal to 1. That means pi j is equal to summation pi k pkj. Okay. So because only one solution is there, that also we have checked. So we only need to check that. Only need to check that this pi is equal to 1 by n by 1 by n 1 by n is a solution. So only thing we have to check is that this 1 by n comma 1 by n comma 1 by n satisfy this. That is the only thing we have to check. Because if it satisfied from the last theorem, because that is the unique solution pi, so therefore this uniform distribution will be a solution. Now since W stochastic, so uh, pi j 1 by n, we are plugging in summation k 1 by n from here, p okay, kj, okay, pkj. Now this is 1 by n summation k pkj, but we know that because it is a doubly stochastic TPM, okay, and p is regular TPM and doubly stochastic also, okay, because it is doubly stochastic, this summation will be 1 because doubly stochastic TPM. So therefore this will be 1 by n. So we have checked that this pi is satisfying this equation. Okay, so therefore this is the solution. Uniform distribution is the solution for a regular TPM, which is doubly stochastic also. Yes, any question here? Let us take an example. Let yn be the sum of n independent rolls of a fair die and consider the problem of determining with probability, with what probability yn is a multiple of 7 in the long run. So let we define xn be the remainder when yn is divided by 7. So yn is basically multiple of 7. So what value xn can take?
0 to 6.
Yes. So xn can take value 0, 1, 2 up to 6. Okay. So xn basically is a Markov chain basically here. So xn is a Markov chain with the states 0, 1, 2, 6. And TPM is, we want to determine the TPM also. So 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6. Now, let us say the remainder is 0. Given that the remainder is 0, now in the next step will be yn plus 1. That means sum of next, basically, let us say we are adding, let us say we are adding 1. Okay, let us say that because remainder is 0, that means 7 is there, 14 is there, these values are there basically in xn. xn plus 1, we are, let us say we are adding 1. So 7 plus 1 or 14 plus 1, 8. So we are dividing by 7. Okay. So what is the probability that we will get 1? Kindly mute yourself. So what is the probability that we will get 1? If we are rolling, in the next step, we are getting the remainder 1, xn plus 1, because xn is, let us say 7. xn plus 1, the remainder is basically 0. That means yn is 7. yn plus 1, that means is, let us say 1 is coming in the next roll, because one more term we have to add after rolling a fair dice, because we are rolling the dice and adding them. So 1 will come with probability 1 by 6. Similarly, remainder 2 will come because 7 plus 2. Okay. 9, we divide by 7, remainder will be 2 with probability 1 by 6. With probability 1 by 6, 1 by 6, 1 by 6, 1 by 6. Whether 7 is there, next remain xn, yn is 7, xn is 0, then x, whether xn plus 1 can be 0.
No, sir.
No, that is not possible because either 1 can come, 2 can come, 3 can come, 4 can come, 5 can come, 6 can come. So again, okay, so that means this is 0. In the same fashion, this is 1 by 6, 0, 1 by 6, 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 0, 1 by 6, 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 0. Okay, so in this fashion, the same, we can make the same conclusion like this, that this is the TPM basically. Now, whether this TPM is regular, yes, so it will be regular TPM. Whether it is doubly stochastic,
Yes, sir.
yes, because some in the row, each row, and some in each column is 1. So therefore this is basically, this TPM is regular and doubly stochastic. Because it is regular and doubly stochastic by the last result, because you can easily check that p square basically have all the elements positive. So that means that is, this is regular. Now the, what is the limiting value? That will be 1, because 0, 1, 2, 3 up to 6, 7 states are there. So 1 by 7, 1 by 7, so on to 1 by 7. That means the long run, the Markov chain will be in state 0 is 1 by 7 and so on. So Yn is a multiple of 7 if and only if xn is 0. So therefore, the limiting probability that Yn is a multiple of 7 is 1 by 7. Okay, so this is the basically the answer here. That means the limiting probability that Yn is a multiple of 7 is 1 by 7 here. So limiting probability means that the process has been in operation for long duration of time. The probability of finding the process in that particular state, irrespective of the starting state. So that is basically the interpretation here. Now, so now the same example you may consider where this let us say this example A. Here we have taken mod of 1 minus A minus B less than 1. So if A and B are 0 and AB are 1, then so what behavior we can observe here? So then, so if AB are 0, then TPM is 1 0 0 1 I. Okay, so what will be P square? That will be I into I. That is again I. Pn will be again I. So chain never change states and transmit. So if we are transmitting some digit, it is received as 0 is 1. If it is some digit is we have transmitted 1, it is received as 1 is with probability 1. Okay, so the chain here never, so in this case, the chain never changes states and transmitted digit is correctly received after n steps also. So now if A is equal to B is equal to 1, then P is 0, 1, 1, 0, then P square 0, 1, 1, 0, 0, 1, 1, 0, that means 1, 0, 0, 1. P cube is 0, 1, 1, 0. That means P into P. P square means P into P. P cube is P square into P. Okay. So therefore, Pn will be 1, 0, 0, 1 if n even, 0, 1, 1, 0 if n odd. So Markov chain has interesting behavior that starting with state 0, we return to state 0 after even number of steps. So that means time between visits exhibit a periodic behavior. So we can check that such type of chain is basically periodic Markov chain. So this is basically periodic Markov chain. And what is the period? With the period 2. We can also check this 0, 1. So 0 to 1 and 1 to 0. So what is the period of state 0? GCD of 2, 4, 6. So on, this is 2. Also D1 is also same. So this is periodic with the period 2 Markov chain. Okay. So here you can easily see that the limiting probability does not exist here. So here in the second part, the limiting probability does not exist. Okay, but we may find out pi is equal to pi p. So, but stationary probability distribution, we may find out. Probability distribution pi is equal to pi naught comma pi 1 and pi is equal to pi p and pi naught plus pi 1 is 1. So this implies that our pi naught is equal to pi 1 from pi is equal to pi p, because pi naught comma pi 1 into p 0 1 1 0, that means pi naught is equal to pi 1 and pi naught plus pi 1 is 1. So this implies that pi naught is equal to pi 1 is equal to half. So stationary probability distribution half comma half is there, but limiting probability distribution does not exist here. Okay, so this was about yes. So
Sir, can you explain once, sir, what is the significance of stationary probability distribution?
significance is only lies when we are studying, because for the regular TPM means that because we know that if we have a aperiodic, that means period is 1, irreducible finite state Markov chain, then that implies that TPM is basically regular. Finite state aperiodic irreducible Markov chain is regular. So That means for this type of chain, Markov chain, the limiting probability and stationary probability distribution are same. This is the theorem. Okay. Just we are saying that if this kind of solution exists, that is basically known as the stationary probability distribution. Okay. And limiting probability is basically we have defined in terms of limit. Basically, that means in the long run, what will happen basically, that is the limiting probability distribution. Now, to solve basically these, finding out this limiting probability distribution, we are using these kind of equations. Okay. If we go for, because we have studied for a periodic, irreducible, finite state Markov chain, if we go for studying the periodic Markov chain, okay, then sometimes limiting probability distribution does not exist. Sometimes some states will be there such that the, let us say that this state is there and this state is there. These are, let us say, 0, such that this is recurrent and aperiodic. And let us say this is recurrent and aperiodic. But in totality, that is because these states cannot be visited here. Okay. So this may be sometimes, some states may be periodic also. Okay. So for studying these kind of things, recurrent and aperiodic, and this is sub TPM, then we can solve where pi is equal to pi p and try to find out the limiting probability using stationary probability distribution here. But this is the significance basically only to finding out the limiting probabilities basically. Because in general, if we go, because Markov chain cannot be maybe reducible also, because it is irreducible. If we go for reducible Markov chain, then some states may be periodic, and for periodic Markov chain, limiting probabilities will not exist, because that will not converge basically. Each step that will be different. For example, we have seen here. So we may, stationary probability distribution usefulness lies basically for finding out the limiting probabilities with the help of stationary probability distribution. Is it okay?
Yes, sir.
Yeah, because these simple cases we have studied, but for reducible Markov chain, we may have some different situations where some classes will be formed. Some classes are recurrent, some classes are transients. So for each class, we have to see separately and find out whether we can find out their stationary probability distribution for that class. And then somehow we have to find it out the limiting probability. For periodic, we cannot find out. Okay, now let us take some example. Okay, so what is basically F11 or F1?
So the probability,
yeah,
the probability of visiting one state in the first step for the first time.
No, it is probability of ever visit, ever visiting state I, starting from state 1 for the first time basically. So this will be basically FF1 plus FF2, so on, these kind of things. So this is the basically starting with one probability of uh, ever visiting state 1 basically. Okay, this is basically in the first step we are visiting. Okay, so this is now similarly we may find out, as we are finding out these values, we may find out f, let us say 2 comma 1. So starting with this is the probability of starting with the state 2. We want to visit ever visiting state 1. In between we cannot visit state 1. Okay, first time visit, yeah, first visit to, yes, you are saying basically you are saying right, that means first visit to state 1, yeah, it may be in one step or two steps or so on, yeah. So first visit basically, yes. So this is the first visit to, starting with state 2, first visit to state 1. It may be in one step or two steps or three steps. Okay, so in between we cannot visit state 1. So let us take some example and try to find out this. Let us take this 0, 1, 2, 3, 4. Okay, let us take this as 1, P, P, and P, Q, 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 1. Now, so let us say F21, starting with 2, we are try to visit state 1 for the first time. So it may be one step, probability is Q. In two steps, PQ square. Similarly, in three steps, PQ, no, sorry, this is not in three steps, basically, yeah, three steps already done. After that, in one step it is possible, in two steps it is not possible, in three steps it is possible, four steps not possible, five step, P square, Q, cube, and similarly P cube, Q4, and so on. These are the possibilities basically. Now, this is Q plus PQ, Q plus PQ square, plus so on. This is Q plus PQ. This is again F2 comma 1. So this will implies that F2 comma 1 is Q upon 1 minus PQ. Let us say that if P is, if P is 0.4, then F21 is 0.6 minus 1 minus 0.6 into 0.4. That means 0.6, 1 minus 0.24. .78. Okay, so this is the probability of, starting with state 2, first return to state 1. Okay, so that if P is 0.4, this is 0.78. So can anyone solve this using Gamble-Student problem? Same thing I want to find out. F21. So F21 so because 2 basically Gamble student, this becomes 0, this becomes 1. Okay, this becomes 2, this becomes 3. Because if it goes to 3, it goes to basically 4. It goes to 4, equivalently this becomes 3 here. Then it will be stuck there. And if we make this 1 as 0, then first basically we want to read for the first time we want to come. Okay, that means this is also basically becoming in the Gambler's ruin problem absorbing state. So start with 1, go broke, goes broke before reaching 3. So in the Gambler's ruin problem, this F21 can be written like this, probability of this. So probability of this will be 1 minus probability of reaching 3. Start with 1, reaching 3 before he goes broke. So that will be 1 minus Q by P raised to power I, 1 minus Q by P raised to power N. Okay, so therefore this is 0.78. So in this fashion, this can be written finding out using Gambler's ruin problem. Is it okay?
Yes, sir.
Okay. So let us stop here. So next time we will see the mean time spent in the transient state, and then we will go for maybe for the branching process. Okay.